Swayam Prabha. Digital India. Educated India.
Good morning. Today I'll solve some problem on gas turbine cycles. Here is a problem on regenerative cycle, that is heat exchange cycle. Let me state the problem number one as a heat exchange cycle is designed with the following specification. The compressor pressure ratio is 5. Turbine inlet temperature is 1200 K. Isentropic efficiency of compressor eta C being 0.85. Isentropic efficiency of turbine eta T is equal to 0.87. Mechanical transmission efficiency eta M being 0.99. Heat exchanger effectiveness is 0.85. The pressure losses in different components are given below. Combustion chamber del PB as 2% of delivery pressure. Heat exchanger air side del PHA is equal to 3% of compressor delivery pressure. Heat exchanger gas side del PHG is equal to 0.04 bar. Ambient condition are giving as 1 bar and 300 K. Evaluate the specific work output and thermal efficiency of the heat exchange cycle. I have indicated here the schematic of a regenerative cycle, that is a heat exchange cycle, along with its operation in TS diagram. C stands for the compressor, while T represents the turbine. HE indicates heat exchanger along with a combustion chamber. Air is compressed in the compressor, then it is passing through the heat exchanger where it is preheated before entry to the combustion chamber. And then the fuel is burned, and thereby high temperature and pressurized gas is expanded to the turbine. Now the turbine exhaust temperature is much higher than the outlet temperature of the compressor, and thereby the energy which is carried by the exhaust gas is being utilized in the heat exchanger. Thereby the fuel input or the energy input in the combustion chamber would decrease and increasing the efficiency of the cycle. Here in the TS diagram, I explain what I have told. 1, 2, which is the dotted line, indicate the compression of gas, compression of air, 1, 2, which is indicated by the dotted line, illustrates the compression of air in the compressor. 2, 5 is the preheating of air before combustion chamber because of heat exchanger. Energy added in the combustion chamber is represented by 5 and 3. Look, del PB indicates the pressure loss in the combustion chamber, where del HA is the pressure loss in the heat exchanger air side. Similarly, 3-4 expansion in the turbine, while del PAG indicates the pressure loss in the gas side of heat exchanger. Thus, 1, 2, 3, 4, and 1 represents the regenerative cycle, and here the heat transfer occurs because of heat exchanger is 2, 5, while the heat added in the combustion chamber is 5 and 3. Now let us solve the problem. I'll start with the compressor. So here T01 must be equal to TA, atmospheric temperature, and P01 is equal to PA, and gamma A is equal to 1.4. This data we know. Therefore, P02 minus P0A, that is total temperature rise in the compressor, can be given by TA divided by eta C within the bracket, P02 by PA to the power gamma minus 1 by gamma minus 1. This relation I have already proved. Now here TA is 300 and eta C equal to 0.85 and pressure ratio is equal to 5 and gamma 1.4. So if I substitute all the value, then T02 minus TA would be equal to 206.05. Now, the compressor work per unit mass flow of air would be WC is equal to CPA T02 minus T0A divided by eta M. Here, the mechanical efficiency is given as 0.99. So we know CPA is equal to 1.005, T02 minus T0A just we have calculated, which is equal to 206.05 divided by mechanical efficiency 0.99. If you do this calculation, it would be equal to 209.17 kilojoule per kg. Thus, WC I have calculated as 209.17 kilojoule per kg. Now, look, P03, that is pressure inlet to the turbine, can be given by P02 within bracket 1 minus del PB, pressure loss in the combustion chamber, divided by P02 minus del PHA divided by P02, that is loss in the heat exchanger air side. Now one is stated as 2% of P02 and another is stated as 3% of P02. Thus I can write 1 minus 0.02 minus 0.03 multiplied by 5. So P03 I have got as 4.75 bar, P01 being 1.0 because atmospheric pressure is stated as 1 bar. So thus here I have calculated T02 minus TA and then WC, and then I have evaluated P03. Note, I have already told P04 will be greater than atmospheric pressure PA by the amount del PHG. Del PHG is the pressure loss in the heat exchanger gas side. Thus I have written here P04, which is the pressure at the exit of turbine, is equal to PA plus del PHG. PA is equal to 1 bar, and this is equal to 1.04 bar. Now, for the turbine, I should use as gamma G as 1.333. Now, T03 minus T04, that is, temperature drop in the turbine, can be evaluated as eta T to T03 within bracket 1 minus within bracket 1 divided by P03 by P04, that is pressure ratio in the turbine, to the power gamma minus 1 by gamma. This expression I have also derived while illustrating the flow through turbine. Now here eta T is given as 0.87. P03 is the maximum temperature of the cycle, which also stated as 1200 Kelvin. P04 are calculated as 1.04 bar. P03 also have evaluated as 4.75 bar. Thus, all the quantities are known now. Now, if we put all the value of P03 by P04 and eta T and T03, I have done over here, and T03 minus T04 would be 329.9 K. Now, I can calculate WT to turbine work per unit mass flow rate has been evaluated as WT equal to CPG into T03 minus T04. T03 minus T04 is the actual temperature drop in the turbine, and CPG value is 1.148. T03 minus T04 have just calculated now as 329.9 K. If you do that multiplication, you will get 378.73 kilojoule per kg. Thus, I have evaluated turbine work as 378.73 kilojoule per kg. Now, the net specific work output would be equal to WT minus WC. Earlier, I have evaluated WC. Now, I got WT. So, net specific work output W would be equal to 169.6 kilojoule per kg. Now, let me do the heat exchanger side. The heat exchanger effectiveness epsilon can be stated as T05 minus T02 actual heat transfer divided by maximum possible heat transfer that would be T04 minus T02. T04 is the exhaust temperature that equal to 0.85. Now I can calculate T02 that I have already done earlier, would be equal to 206.05 plus TA. Similarly, I can calculate T04 from here. You see, T04 is equal to T03 minus 329.9. If I now evaluate, you know the atmospheric temperature is 300 Kelvin, so we can evaluate T02 and T04. Now T02 would be equal to 506.05 Kelvin and T04 would be equal to 870.1 Kelvin. Now, if you put the value of T02 and T04 from this expression of heat transfer effectiveness, I can get T05. Now, I can write T05 is equal to T02 plus epsilon into T04 minus T02. All the quantities are known here. So T02 is equal to 506.05, epsilon equal to 0.85, within bracket 870.1 minus 506.05. If you do the calculation, T05 would be 815.5 Kelvin. Thus, heat addition Q is equal to Cp into T03 minus T05. I know T03 as 1200. T05 I have evaluated as 815.5. Cp I know as 1.148 for the gas. Thus, Q I have evaluated as 441.4. That is 441.4 kilojoule per kg. Thus, thermal effectiveness would be equal to W divided by Q. Now, W I have evaluated as 169.6 and Q as 441.4. So, thermal efficiency would be 38.4%. Okay, so here I have stated what I've got. That's the answer. The specific work output is equal to 169.6 kilojoule per kg and thermal efficiency as 38.4%. I'll now solve the second problem on a reheat cycle. The statement of the problem is the following data refers to a single shaft gas turbine cycle with reheat. The power generated is 235 megawatt at 300 K and 1 bar. Compressor pressure ratio is given as 30. Isentropic efficiency of compressor eta C equal to 0.87. Isentropic efficiency of turbine eta T is 0.9. Turbine inlet temperature, both the turbine, is 1500 Kelvin. Pressure loss in first stage compressor del P divided by P02 is equal to 0.02. Pressure loss in the second combustor is equal to 0.04. Exhaust pressure is given as 1.02 bar. Fuel air ratio is 0.034. Calorific value of fuel is 43,100 kilojoule per kg. Now we'll have to evaluate the mass flow rate of air, specific fuel consumption, thermal efficiency of the cycle. I have indicated here the schematic of a reheat cycle where C represents the compressor, HPT indicates high pressure turbine, LPT being low pressure turbine. So air is compressed in the compressor, then it is heated in the combustion chamber and high pressurized and temperature gas is expanded in high pressure turbine, and then again it is reheated and then expanded through low pressure turbine. State point has been denoted at 1, 2, 3, 4, 5, and 6, and the operations of the reheat cycle is presented here in the TS diagram, where 1, 2 represents the actual compression of air, 2, 3 the heat addition in the combustion chamber with a pressure loss del PB. Similarly, 3, 4 is an expansion in HPT, and 4, 5 reheating of gas in the second combustor with a pressure loss del PB. 5, 6 expansion through low pressure turbine. Now, after explaining the TS diagram, I can say T01 is equal to TA and P01 is equal to PA. TA and PA be the atmospheric pressure and temperature, and gamma of air can be considered as 1.4. Therefore, the temperature rise in the compressor can be stated as T02 minus TA is equal to TA divided by eta C, or then bracket P02 by PA to the power gamma minus 1 by gamma minus 1. P02 by PA is the compressor pressure ratio. Eta C is the compressor efficiency, isentropic efficiency, and TA being the atmospheric temperature. So I have put all the values here. 300 divided by 0.87 within bracket 30 to the power 1 by 3.5 minus 1. When I have calculated this, I got T02 minus TA is equal to 566.42 K. Thus, I can evaluate work required to run the compressor WC as Cp into T02 minus TA. That's 1.005 into 566.42. Thus, I have got 569.3. Thus, a specific work required for the compressor is equal to 569.3 kilojoule per kg. Now P01 is equal to 1 bar given, so P02 would be 30 bar. Now P03, that is total pressure at the state point 3, is equal to P02 with the bracket 1 minus del P divided by P02, that is equal to loss in the combustion chamber. It's given as 0.02, that I have got P03 as 29.4 bar. Furthermore, P06, that is total pressure at the state point 6, is given as 1.02 bar. Now I can say that theoretically the optimum pressure ratio for each turbine would be root over P03 by P06. I know total pressure at the state point 3 and I know total pressure at the state point 6. Just I can evaluate root over P03 by P06, which has given me 5.37. That means work output would be optimum when the pressure ratio for each turbine would be around 5.37 bar. Now I'll show you how I have arrived this conclusion that the optimum pressure ratio for each turbine can be evaluated by root over P03 by P06. With respect to that, I have referred back to the TS diagram. I have already told that for optimal condition, pressure ratio for each turbine would be the same. That means pressure ratio in HPT must be equal to LPT. Further, T3 is equal to T5. Now let us consider the pressure ratio of each turbine can be designated by small r. Thus I can write P3 by P4 is equal to P5 by P6 is equal to R. Now P3 by P6 can be written as P3 by P4 into P4 by P5 into P5 by P6. Now P4 and P5, they are approximately equal. So the ratio of P4 by P5 I have considered as unity, and P3 by P4 is equal to R, and similarly P5 by P6 also is equal to R. Thus I can get P3 by P6 is equal to R squared. Therefore I have written a for optimum condition, pressure ratio for each turbine can be given by root over P03 by P06. After getting the pressure ratio on each turbine, I can evaluate the temperature drop. Thus, let us assume P03 by P04 is equal to 5.3. Hence, temperature drop in high pressure turbine T03 minus T04 is equal to eta T into T03 within bracket 1 minus within bracket 1 divided by P03 by P04, that is pressure ratio in HPT to the power gamma minus 1 by gamma. I know eta T is equal to 0.9, T03 is equal to 1500, P03 by P04 is 5.3, and gamma minus 1 by gamma becomes 0.25. If I put all the values and the calculate, then T03 minus T04, that's temperature drop in high pressure turbine, would be 460.26 Kelvin. Now, P05 can be evaluated from P04 as the loss in the reheat combustor is known as del PB by P04 is equal to 0.04. Thus, I have evaluated P05 is equal to P04 into 1 minus 0.04. Now I'll have to evaluate P04 that I can get from the ratio of P03 by P04. I know the value of P03. P03 is equal to 29.4. Thus here I have evaluated P04, which is 29.4 divided by 5.3. That becomes 5.547. Hence, now P05 can be evaluated as 5.547 into 0.96. That is 5.33 bar. Now, T05 minus T06, that is temperature drop in LPT, is equal to eta T into T05 within bracket 1 minus within bracket 1 divided by T05 by T06 to the power gamma minus 1 by gamma. Here eta T is equal to 0.9, T05 is 1500. The pressure ratio P05 by P06 is nothing but 5.33 divided by 1.02. So if I evaluate this, I'll get temperature drop in the LPT as 457.1. Please note that the temperature drop in HPT almost equal to that of LPT. Now turbine work would be the combination of HPT and LPT. Thus WT is equal to CPG into T03 minus T04 plus T05 minus T06. The T03 minus T04 is the temperature drop in HPT, and T05 minus T06 represents the temperature drop in LPT. Thus, I know both the value. One is 460.26 and the other one 457.1, and CPG equal to 1.148. Therefore, if you do the multiplication, you will get WT is equal to 1053.13 kilojoule per kg. Now the net work output would be W is equal to WT minus WC. I have already calculated the value of WC. Then W I can get as 483.83 kilojoule per kg. That means this is the specific work output of the cycle. Thus now I can find out the mass flow rate of air required. If it is M, then M would be equal to power developed divided by specific work output. It has been stated that power developed is 235 megawatt. The megawatt I have converted to kilowatt, and I have divided by specific work output, that is 483.83, and thus I have got M is equal to 485.71 kg per second. So I have evaluated mass flow required of air. Now specific fuel consumption can be evaluated from fuel air ratio. So SFC is equal to 3600F by W. W is equal to specific work output, that is 3600 into 034 divided by 483.83. It is equal to 0.253 kg per kilowatt hour. Now efficiency can be evaluated from specific fuel consumption, which is equal to 3600 SFC into del H. Del H is equal to calorific value of fuel, that is 3600 divided by 0.253 into 43100. If you evaluate this, it will be 0.3301. Thus, I have got all the required values, and the answers are mass flow rate of air equal to 485.71 kg per second, specific fuel consumption as 0.253 kg per kilowatt hour, and thermal efficiency as 33.01. Thus, I have solved two problems in details, one on regenerative cycle and one on reheat cycle. I trust the similar problem you'll be able to solve. Thank you for listening.